Really glad that you're here this morning. This is the beginning of some really important regional dialogue that we're interested in having around our solid waste system planning. This is a very focused segment of a broader dialogue that ultimately is going to take place. But we're glad that you're here because as we're getting ready to release our first draft comprehensive plan, we're going to need to really expand the realm of possibilities when we're thinking about our long-term disposal options. Our Cedar Hills Regional Landfill is presently going to reach its capacity in about 2028. And so we have some options available to us. We could develop additional capacity. We could export our waste on rail to an out-of-county landfill, or we could develop a waste-to-energy solution. We know a lot about landfilling. We're doing it for over 50 years. We've got a fairly good insight around regional rail activities for waste because the city of Seattle and Snohomish County do that. But we didn't know enough about waste-to-energy to really have that informed dialogue. And so the county hired Normandeau and Associates to lead an in-depth study on our options. And basically we asked a very, very direct question. We said, what is the best waste-to-energy technology for King County? What's the best one and why? And what are the implications of that? Because should we select that as our long-term disposal option, we really want to understand what it would look like here in King County. We know that there are things happening around the world and even across the U.S., but we wanted to know about the possibilities for King County. So Normandeau partnered with other organizations, two of which are here today. You're going to hear from Curt Tolkien here in a moment. He's the Senior Vice President at Normandeau who led this team. He's accompanied with CDM Smith, Paul Hauk. As you'll get to learn right away, Paul is a seasoned veteran in the area of waste-to-energy. He's been involved, as has CDM Smith, for over 25 years in these projects and brings a wealth of hands-on experience there. Actually serves as a judge on the Waste-to-Energy Excellence Panel, part of one of the SWANA initiatives. So Paul is going to do a lion's share of the presentation today, as CDM Smith did so much of the work. But also Neomar was an important aspect of this, and Philip Schmidt-Pathman is also here, and Neomar provided an international perspective on the waste-to-energy elements as well. You're going to hear a little bit about waste export because we again, we know a fair amount about that activity, but had some interest in understanding out-of-county landfill capacity as well as rail capacity. So that was a small but important part of the scope of work that Normandeau and their team embarked upon. This is the beginning of the dialogue. We're going to be focusing on waste-to-energy. I want to turn it over to Curt Tolkien, and thank you, Curt, for the work that you've been leading over the past several months.
Great. Thanks, Pat. So as Pat said, I'm Curt Tolkien, the Senior Vice President and Chief Operating Officer for Normandeau Associates. We are one of the 200 largest environmental firms in the United States. And if you look at just natural resources, which is really our area of focus, we're one of probably the 5 largest standalone natural resource companies in the United States. But having said that, we knew we needed some help to get a very good, solid look at the waste-to-energy facilities, and so we brought CDM Smith on the team, and as Pat said, Paul has a lifetime of experience working there, and Philip and Neomar have done a lot of work in Europe, so we'll get a little bit of a flavor of what's been happening in the United States, what's in the realm of possible in the US and in Europe through the members of the team. So that's our crew for today's presentation, and we're very happy to provide you with this. And with that, I'm going to turn things over to Paul and let him get started.
Good morning, and thank you for the invitation to present our findings on this study. I was actually hoping this meeting would have taken place in September. My wife was dying to come out here with me, but maybe there'll be a future event. So anyways, let me carry on. A word from my sponsor, CDM Smith. We're primarily consulting engineers. We work in the water, wastewater, transportation, environmental arena, and naturally solid waste. As you can see, we have both international and domestic experience. Just recently, the map doesn't reflect this, but we're about ready to wrap up our involvement with the facility in Dublin, Ireland. They just built a brand new 2,000 ton per day facility. And I hail from Tampa, Florida. We have quite a few solid waste professionals in Tampa. We do a lot of work in Florida. Florida has the highest number of waste energy facilities in the United States with 11. So that's a little bit about who CDM Smith is. My career, 27 years ago, after 17 years in the commercial nuclear power business, I decided to do something a little more less complicated but more exciting. And I became involved in a solid waste project as a construction manager. So I showed up for work one day and in less than 3 years helped build a plant just north of Tampa. And so I showed up on day one of that project, but surely there were meetings like this, workshops, part of a feasibility study that all took place years in advance of my first arrival on that project. And so I think this is a similar situation here. This is the beginning of your effort to figure out what you want to do, where you want to do it, how you're going to do it, and when you're going to do it. And those same decisions had to be made by the commissioners of Pasco County, Florida. And sure enough, they did. For the last 21 years, I've been working as a consultant, climbing under, over, around, and on top of these facilities, doing inspections and annual reports and monitoring the performance of the contractors on behalf of the owner, which is cities and counties. And most recently, that's a photo of me at Pinellas County, Florida, where for the past month, I've been averaging about 5 miles a day, walking around a 3,000 ton per day facility that's undergoing a major retrofit. We call them outages. And so, yeah, I do get my hands dirty and from time to time, and I'm getting a little bit too old for that, so I need some young men to take over here. But anyways, moving on, part of the introduction, the U.S. and Europe are in close agreement with the approach to solid waste management and resource management. It's waste prevention, reuse, recycling, maximize recovery of energy and materials, and then minimize landfill. That's the European version. The U.S. version is what I call the 5 R's, reduce, reuse, recycle, recover energy and materials, and then manage the residuals. So just a simple little diagram, but it paints the picture of what we're trying to do. And then this little diagram here on the left, you can see that who's doing the work, okay? Today in America, landfills are predominantly doing the work. 83% of the waste is put into landfills today. What we're really trying to achieve is a paradigm shift where we're turning that pyramid up on its head. We want to do less work in the landfill and more work with the other rungs of the hierarchy. And so what I'm here to talk mostly about today is the waste conversion rung, the third rung. And included in waste conversion, we have waste energy. And so the evolution of this industry, if you look on the second column, there's a line there, a column called incineration. And I know you had a couple incineration plants here in this area along the coast. And they're the ones that gave everyone a bad taste in their mouth. They were the ones that emitted black smoke, and they recovered absolutely no energy. And it was simply a volume reduction technology that came out of the backyard burn barrel, literally. But as you see, the first generation waste to energy, where we started to recover the energy, heat from combustion converted to steam. Steam drives a turbine, makes electricity. And so you can see we had a rudimentary type of air pollution control at that time, electrostatic precipitators. We did have some magnets, some electromagnets to recover the ferrous metals. We hadn't invented or discovered the use of eddy current separators for non-ferrous metals yet. and there was no use for beneficial use of ash. Moving on to the second generation, what I call the modern waste energy facility, that's what most of the facilities today that are operating were built as a second generation facility, a little higher steam pressure, a little higher energy recovery, a more advanced pollution control system, a better magnets. Now we've got eddy current systems that can recover the non-ferrous metals, and we're looking at options for ash reuse. And then third generation, that's today, and there's only one plant in America that's been built, actually two, one in Hawaii, that have been built into that third generation advanced, what we call resource recovery. And you know, ironically, back in the old days, a lot of these facilities were in fact called resource recovery facilities, and then we sort of got away into this waste energy thing. But I always liked the resource recovery term because it more accurately represents and embodies what's going on. We're recovering energy, we're recovering materials, we're recovering minerals, metals, that sort of thing. So a lot of people make their living in this industry, and it's changing and advancing every day. And it's not stagnant. Just because we haven't built very many of these facilities in the last 15 years doesn't mean this industry is stagnant. We are rebuilding these facilities, we're expanding these facilities, they're building them left and right in Europe and China. So we can take advantage of all of that in your situation. You certainly want to leapfrog where everyone else has already been. So just another little diagram showing the sort of trends. We're moving more and more toward improved efficiency, higher energy recovery, moving more into sustainability, where we're using less reagents, using less resources to accomplish the same goal. And then you can see some trends going downward. The air pollution emission profile is a lot smaller than it used to be. Chemical reagents, we're learning how to optimize those things. There's a lot of engineering and scientific talent that it puts into this industry here, and it's paying off. But the last little bullet there is lower payments for electricity sold to the electric grid, and that's the sad news. And I have some suggestions for that. So this is just a short list. I have a long list of benefits of waste energy to the electric grid. And it's centrally located. It's typically in the centroid of the waste. It's in the centroid of the electric demand. It's right where you want it. There's no line losses. There's not a power plant 150 miles off with big transmission towers that have to bring the power into your community. It's in your community. It's base loaded. It's considered renewable in most areas. It delays the need for new units as they retire some of these fossil units. The fourth bullet down, it improves the fuel diversity. And I want to bring to your attention just something I discovered last week. And that is the Department of Energy has recently proposed that any power plant that can store or stockpile 90 days of fuel should be compensated for that attribute, because of Superstorm Sandy and hurricanes and forest fires and things of that nature, or the polar vortex. All of these things are very disruptive on the electric grid. And when the wind doesn't blow and the sun doesn't shine, the renewables aren't going to get you back on the grid. You need baseload power sometimes to recover from these types of incidents. And so the DOE is now proposing, and this is beneficiary to the coal and the nuclear industry primarily, let's be honest. But the fact of the matter is a waste-to-energy plant has an endless supply of fuel, and especially after an extreme weather event. Just in my neighborhood, I live in Tampa, just this Saturday, they finally picked up the rest of the debris that's been on our curbs for the last 2 months after Hurricane Irma. So these natural weather events can really increase the fuel supply, if you will. And so anyways, now I'm going to move into, well, that concludes my introduction. So in following Curt's lead, are any questions over what I just shared with you? Do you want to ask anything at this moment?
My question was that you were talking about this being close to the grid in the community, but the report says you need 20 to 40 acres to build a facility to serve King County. So I made the assumption that sites are being selected and communities being spoken to, or are we just too early to do that yet?
No, again, we weren't really challenged with helping find a site at the moment. The 20 to 40 is a reasonable estimate. I've seen, and it depends on the size of the facility. I saw a facility in Alexandria, Virginia on 3.5 acres, and I swear there isn't a blade of grass on that facility. And you could never do that, again, because today you have stormwater management rules. So typically, 20 to 40 would be a reasonable amount of property. Again, it depends on the size of the plant, and just if we harvest the rainwater and use it in the process, which we'll talk about in a minute, then yeah, you don't need to put so much real estate to use in stormwater treatment and stormwater collection. So I would say 15 acres would, for the type of facility you're talking about, 15 would be press the limits on the low end.
Thank you.
Okay? So now we're going to talk a little bit about your existing conditions here. So in the light blue, that is the waste projection curve from 2028 through 2078. That's a 50-year horizon. And as you can see, it's accelerating. It's growing quite rapidly. And that's basically the waste stream that we're going to work with the rest of our analysis. So the first thing we did was we wanted to evaluate the various technologies that were out there, and so we came up with 9 major criteria, mostly technical, environmental, economic, and then overall risks. So we assigned a point, and the CDM and the county and Normandeau, we all agreed upon this weighting factor. At this moment, we said, okay, these are how we're going to score 8 different technologies. And this is our scorecard, kind of like a summary, and I know you can't read that, and I can't even read it. But basically, we took those 9 criteria, and then we broke them down into 45 sub-criteria. And these are kind of just like checklists for us to go through mentally and say, does this technology satisfy this concern, or how well does it satisfy, or that sort of thing. And so we have 4 technologies that were what we call proven. That's mass burn waste energy, that's combustion, thermal combustion on a movable grate, or advanced thermal recycling, ATR, and that's very similar. That's a lot of, what they call in Europe, oftentimes they call it ATR. And we looked at RDF facilities, refuse-derived facilities, and then gasification technologies and pyrolysis technologies. Those are all emerging technologies. You may or may not have heard of them. And the last column there is a RDF to a cement kiln. And that's a different form of waste energy, and it's been proposed here recently in Vancouver, BC, as one of their options, and it's also employed in Europe too. But anyways, the bottom line is that mass burn, thermal processing on movable grates with a water wall boiler, that's tech talk. But basically, and I'll show you what the grates look like, and the water wall boilers are just tubes that encase everything and capture the heat. Mass burn and ATR were the highest ranked, and so that's what we would recommend for King County to consider today. You don't want to be first on new technologies. You may not even want to be second. You want something that's proven. You want something that's reliable, robust, and has met the rigors of time. And that's what these technologies have done. This is a grate, a modern grate system. This is the furnace of a small boiler. It's provided by B&W. This is their magic grate, which was recently employed in Palm Beach County for the first time. It's called their Dynagrate, and it's very clever. It's water cooled, so that each of those runs, those little, that's an incline. The waste starts at the top and it migrates down, and those grate bars are constantly rotating and moving, just like they call it a stoker, and that's what you would do at your fireplace at home. You would stoke the fire when it starts to burn down a little. You want to agitate it. So these furnaces are constantly agitated. They use alloy metals, and they have Inconel on the walls of the boiler tubes, and this is it. This is an engineer's dream here. We get excited about this stuff. But it represents some major technical breakthroughs. You get far more reliability with a water-cooled grate. You don't burn as hot. You don't melt stuff as much. And on the Inconel, it's like good and plenty. It lasts a long time. Whereas in the old days, you'd have to rebuild your boilers every 3, 5, 7 years. We're getting a lot better life out of these things today. And this is just a simple diagram here showing the the basic inputs, garbage in, some emissions out, electricity out, fly ash and bottom ash, two different sources of ash. They're combined together in America. We recover the metals and the ash goes to a landfill. We have a couple reagents that are used to control NOx emissions and carbon to control mercury and dioxins, and lime to control acid gases. And that's a simple diagram. And this is a cross-section. This is a cross-section of the new plant in Palm Beach County. Fully enclosed, a tipping floor where the waste is received, a pit that stores anywhere from 8 to 10 days worth of fuel, a crane that picks it up and feeds it into a furnace. It flows by gravity onto those great surfaces that I showed you. It's agitated, it combusts thoroughly. The heat's recovered as energy, and then the exhaust gases are heavily scrubbed by a scrubber, a fabric filter, and in this case, what's called an SCR, a selective catalytic reduction technology to further remove some of the NOx compounds. NOx compounds are precursors to smog. It's the pollutant du jour in this industry. It's the last of the pollutants that has to really get more thoroughly addressed, and it is being addressed. And so again, garbage in, you can see a grapple picks up 8 to 10 tons at a grab, and it feeds it into the furnace, and what comes out is significantly reduced in volume and weight, and it's been sterilized and stabilized. And so that ash, when put in a landfill, doesn't create methane, doesn't give off bad gases. As a matter of fact, the leachate from a modern ash monofill almost meets drinking water standards, with the exception of chlorides, salts, and sometimes aluminum. So it's fairly clean material. This is just an energy balance showing that the waste in has a certain calorific input, and of that waste in, we're generating typically 30% of the power is coming off as electricity, and believe it or not, 70% is coming off as waste heat. Now that waste heat represents flue gas, the hot gases coming up the stack, and the cooling tower, the mist that you see coming off from a cooling tower. That's all waste heat, rejected heat from the system. That's the modern day steam cycle. It's not very efficient, but 30% is a lot better than it used to be. But the 70% represents a huge opportunity for combined heat and power projects. And combined heat and power projects are typically done in the northern climates, where you need district heating, where you can use steam for heating cities. Indianapolis is the furthest south. Nashville still has a thermal system, but they use natural gas now. But Indianapolis uses waste, and they provide steam to their heating grid. But most of the heating grids are in the northern climates, and Europe has a lot too. So anyways, that's, again, that's technical talk. This diagram here again shows you that it's just not a garbage truck in and an ash truck coming out. There's a lot of other inputs in the form of the waste, the water that's used, the air, the reagents, and in the case of the outputs, you can see there's bottom ash, glass, ferrous metals, non-ferrous metals. And then in Europe now, they're predominantly starting to really go after some of the other lower value chemicals, but they're still marketable, like metal carbonates and hydrochloric acids, gypsum. You know, all in all, this industry is being taken over by chemical engineers. So if there's any chemical engineers in the crowd, my hat's off to you, because you're going to finish this job. And so, okay, so that really covers the existing conditions for your system. But I will point out that what you have here are 8 transfer stations, 1 landfill, and a privately operated MRF, or several MRFs. So you already have some of the elements, the major elements, I might add, of an integrated solid waste management system. So what we did here is we said, okay, how do we size this facility? And one option is that we could size the facility so on day 1 it's running at full capacity. But what happens is, because now your growth continues over the next, say, 20 or 30 years, you have excess waste now. You have bypass waste, as we call it, waste that has to go somewhere else, whether it's a recycling program or to the landfill. So that was one option that we looked at. Some of the advantages of that is that you're running full steam ahead. You're not throttling your plant. You're always at maximum power. You have a smaller facility, lower capital cost, and it forces you to have to deal with your excess waste in some other way, i.e. recycling. That would be the preferred option, or at least that's what people would tell you. So the disadvantages include you have excess bypass waste that you have to now deal with, and it eliminates the opportunity for a regional project, because now you don't have any other capacity to offer any of your other communities that may want to send waste your way. And it also eliminates the opportunity for marketing of that excess capacity for what I call special waste. And I'm going to talk at length about special waste later. But anyways, those are the advantages and disadvantages. We didn't select that approach. We chose instead to do what we said, eliminate bypass waste. We were going to size the facility so that it was over capacity. It had excess capacity on day one, and it was at full capacity at the end of its financing period, whether that was 20 or 25 or 30 years, okay? And so now that results in a bigger facility, a higher capital cost. It gives you excess growth to grow into, gives you excess capacity to market to your neighboring communities or to special waste programs. So that's what we chose, and I'm going to show you now illustratively the diagram on the left. You can see that's your waste projection curve there in red, and that blue line there represents the size of the waste energy plant, in this case 4,000 tons per day. That line there intercepts that line in year 20. So all the area you see from here, underneath here, is excess capacity that you either can use to your advantage or just run your plant at a lower rate. And over here on this diagram, this basically shows you that you have excess capacity early on, and as time grows and your waste stream grows, you're slowly converging on where those 2 points meet. So this is a 20-year scenario, and in this particular case, that initial size right there has 29% excess capacity. Okay? So then looking at the 30-year scenario, same story. Only in this case, you're looking at a longer horizon, and where those two lines meet now requires 4,500 tons per day plant. It's a bigger unit, costs more, and again has a lot more capacity, unused capacity that you could in fact market, or it's idle. And then looking at a 50-year scenario, in this case we went to the midpoint, 25 years, sized the plant for the 4,200 tons per day, and then in year 25 added another, whether it's a new plant or additional capacity remains to be seen, but 2,300 tons of capacity is added. Did I do that right? 4,200? This is 63. 2,100 tons a day of additional capacity are required midway through in order to intercept that growth curve at year 50. And so again, you see excess capacity declining over time. The new unit comes on, or the expanded unit comes on, excess capacity until you get close to the end. So those are the three scenarios that we looked at. And just to give you some comfort about the size of these facilities, you're not the first. There's a facility in China that's under construction today that's being built for 5,612 tons a day, 6 units. It's using that B&W technology that I showed you a picture of that was also employed in Palm Beach County, Florida. So that's a very similar unit there. Palm Beach County was the last plant built in America in 2015. It has 3 units of B&W, 1,000 tons per day each. Honolulu expanded recently with 1 unit, 900 tons a day. It uses Martin GmbH out of Germany. It's been in operation for the last 5 years. Pinellas County, Florida, that's like the granddaddy of these facilities. It was built in 1985. That's why we're spending so much time there now. is putting Humpty Dumpty back together. It's 37 years old. It has 3 Martin mass burn units at 1,050 tons a day. Delaware Valley, Pennsylvania has 6 rotary combustors. They don't make them anymore, but nevertheless, they're there, and they have a total capacity of 3,510. So there's a lot of large plants out in the world that what we would call reference plants. So you don't have to be frightened that you're stepping out into the Netherland where no one else has been. Also, make a note of this, that the last 2 plants in America, projects, were done by communities that already had a waste energy plant, and it was an RDF type of technology where they processed their waste through shredders and conveyors and magnets and things of that nature. And they chose not to pursue RDF technology, and they went to the mass burn option. So again, this is very much in line with the way we feel. The mass burn technology is proven worldwide in 1,000 installations. There's a lot of people that are making it better every day. That's where you want to be. I'm going to talk a little bit about some of the benefits that we've discovered through all our research on these other communities that own these plants. Combined heat and power, we mentioned Hennepin County, Minnesota, Indianapolis. That's both of those provide steam to district heating loops. Durham, York, BC, that was a relatively new plant built in Canada, and it doesn't currently provide steam to a district heating system, but it was designed to allow that. And then Dublin, the project I mentioned to you earlier, just went online here. Internal use of electricity, Hillsborough County, Florida, that's where I live. It surrounds Tampa. And then Lee County, Florida. Both of those facilities use as much power as they can for their own campus, their recycling solid waste campus. And it's not a lot of power. It's 2 megawatts in Hillsborough's case, probably less in Lee County's. But what it represents is cities and counties not taking it on the chin anymore just because they're getting paid less by the utilities. They're going to find a way to get some better benefits out of their projects. And in this case, I'll show you a little photos earlier or later. Recycling of landfill leachate and stormwater in the waste energy process. This is Pinellas County, St. Petersburg, Florida area, and I'll show you a photo of this particular project, but this could be a project very similar and something that you might be interested in, given that you have a landfill that also has a lot of stormwater and a lot of leachate that you're currently passing on down to the wastewater plant. And the same situation in Florida, but I'll show you what they did instead. And then co-combustion of tires, used oils, auto shredder residue, wastewater treatment plant biosolids, bulky and construction waste, Honolulu. If you want to go see a razzle-dazzle plant, Honolulu would be a place to go. They just put all of that into play with their 1 new expansion unit in the last couple of years. But you can see they're burning a lot of special waste and co-burning, co-combusting, and it works very well. C&D waste, Lee County, Florida. The county actually built a construction and demolition recycling facility so they could mine the combustible fraction from it to put into their waste energy plant because they had additional capacity or they needed more fuel. And so they decided on their own to go into a marketplace that was typically served by the private sector, C&D waste. So there's an example there. And then this is a moneymaker here, co-combustion of special waste in need of assured destruction. And that's USDA regulated garbage. That's what they call it. I didn't make it up. They call it regulated garbage. We call it international waste. It comes off your international ships, comes off the marine bases or military bases. Any international waste has to be processed in some special way. And so you can charge $100 a ton or more, or $200 a ton. Medical waste, solid waste, and liquid waste. Believe it or not, you can process liquid waste in a waste energy facility too, up to a certain amount. And so there's some of the facilities that are doing that special waste: Honolulu, Tulsa, Oklahoma, Huntsville, Alabama, and numerous other facilities. So the point I'm making is each waste energy facility owner over time has found ways to add benefits, to increase revenues, and to make their process more friendly to their community. This is the Pinellas County example I want to share with you. There's a pond up here, 3, It stores 100 million gallons of water from the landfills. There's a landfill here, here's a landfill here, and there's probably one back here. And all of that water is then sent to the water treatment plant. They built this right here 3 years ago at a cost of $15 million. So they're treating 1.5 million gallons of water from that pond there, and they're feeding it to the waste-to-energy plant as processed water for cooling, for boiler water makeup, that sort of thing, for fire protection. So here's an example of a community that is very similar to what you have. You have a landfill, you have a pond or a series of ponds, you have treated waste or leachate, and what you don't have is a waste-energy plant or a water treatment plant. You're sending it to your neighboring wastewater plant. But anyways, it's an example, real world, in motion. So, summary of the features that we would propose for King County. Advanced combustion on movable grate with water wall boiler. That's mass burn, okay? Today they have expert combustion control systems. What does that mean? That's like autonomous vehicles that we're hearing about today. That's like those jets that Boeing built. That's like your cars today. All the sophistication, the instrumentation, the anticipatory controls. It's being applied universally, including in this industry. Medium steam pressure, we're going to generate 609 kilowatt hours per ton. Advanced pollution control system, just like Palm Beach County with the exception of SCR. We're not proposing SCR technology just yet. That would be a decision for the community. But Palm Beach, I'll tell you, it wasn't Palm Beach's preferred solution. They sort of were pushed in a corner by the Florida DEP on this. But anyways, they did. They went along with the SCR, but we're not proposing that for you this time. It's just a standard, normal, advanced air pollution control system that works today in America. Advanced metal recovery. Now, Palm Beach County does not have an advanced metal recovery system, but this is widely deployed in Europe. It's being implemented here in the States. Spokane's ash is being processed by a company called Lab USA in Roosevelt, Washington, and they're taking all the ferrous and non-ferrous metals out of their ash at a remote site, okay? So there's a couple vendors from Europe that are over here saying, we know how to take apart your ash stream, and we can recover the metals quite nicely. Rainwater harvesting, air-cooled condensers, zero liquid discharge to minimize demand on local water supplies. We would definitely promote that no matter where we go today. Water is just too critical to just use randomly. And then fully enclosed, architecturally pleasing building and landscaping. That's a snapshot of what we think would work nicely here in King County. The same diagram we showed you before, just a refresher. Fully enclosed, mass burn, thermal combustion, modern day air pollution control system. That's a rendering, Palm Beach County. That's a 2 million gallon storage tank. We harvested the rain from 7 acres of roof. So let's call this an industrial scale rainwater harvest system. Probably never done anywhere else in the world at this size. So that tank there stores enough water to meet the demands of this facility 15% of the year. Architecturally, it's quite nicely jazzed up. The chimney is not too much, nothing too architecturally unique about it, except that it's oblong, so it had a lower profile or a slimmer profile when viewed from the north. It has an air-cooled condenser, so it doesn't use a lot of water for cooling. And cooling towers typically are what you see that give off big plumes of steam, which, you know, a lot of people don't appreciate that either. So anyways, that's a rendering, a view from a different angle. In this case, they have an education center with a sky bridge over to the plant. And that was all of this, by the way, CDM Smith did the architectural design on this plant and all the civil site design. So I think maybe I didn't mention, the Pasco plant was the most exhilarating thing I did in my career. Well, this was the second most exhilarating thing. I was on the proposal team where we worked with B&W and won this job. So, but I didn't have my hands on it like I did at Pasco. I was still, just wasn't involved with the construction. But nevertheless, you can see it is quite nice. This particular plant, there's an existing 2,000 ton per day RDF facility, and then right beside it is the new 3,000 ton per day mass burn unit. A close-up of the education center, it's LEED platinum. It has a solar canopy on the parking lot. It too has a rainwater harvest tank. It's back here, you can't see it. In Florida, you can do a lot of instant landscaping overnight, boom. So it's quite nicely done. The tipping hall where the trucks come in, and remember I said that you have 8 transfer stations. Well, in Palm Beach County, they have 6. And most of their waste is delivered in very large transfer trailers, much like yours. And so this tipping hall has 24 truck bays. This tipping floor is as long as a football field, including the end zones. That is supersized. I've never seen anything like that anywhere, but nevertheless, Palm Beach County thought that that was appropriate for their system. The site is very nicely compacted, 24 acres. This one is on 24 acres, which includes stormwater treatment. Over here, there's a pond that doesn't show, but notice the dimension here of 1,000 foot by 1,000 foot. That's essentially the footprint that this facility was built on, and I'll just remind you that you have a 1,000-foot buffer around your Cedar Hills landfill, okay? So I'm just dropping a hint. 1,000 foot, we can squeeze it in. Actually, we can probably even make it tighter, but Palm Beach County has an advanced air pollution control, which includes that SCR, selective catalytic reduction. That's for the chemical engineer in our crowd. And they use catalysts to basically convert NOx compounds into elemental nitrogen. So it's all nicely designed and built by B&W. They do all that kind of work. And that's their emission profile. You can see all the pollutants that are regulated. You can see their limits. You can see their test results. For the most part, they operate very well below their permit limits. The only one that gets close is the NOx, and in their case, their limit's 50 ppm, and they're up around 30, 31. So they're at 60% of their limits in terms of NOx. But all the other plants, their permit limits are 200. So you can see that the NOx limit has really been ratcheted down. And I'm going to pause here. Philip's going to come up and talk a little bit about European technology, but does anybody here want to ask any questions on what I just presented? Go.
I'm sorry, here you go.
Thank you. Regarding the inert ash,
Yes.
back on slide 20, in your studies and discussions, did you talk about that ash going to road beds? Road beds.
Yes, and I'm going to get to that after Philip's part of the presentation.
Okay.
So yes, there's a number of ash recycling technologies that might fit in very well here, and we will get to that in a minute. Anybody else want to ask a question? Yes, sir. Or yes, ma'am.
Could you talk about the life of the equipment you're proposing to build? How long would that last for the initial construction?
Yeah,
And the life of the equipment?
That's a good question. You know, some pieces of equipment wear out in 5 years, some of them go 20. And again, it depends a lot on the level of quality that you build into the plant at the onset. The boiler tubes, depending on what part of the boiler they're in, they can be replaced on a 5-year cycle, a 7-year cycle, or now we're seeing 10-year cycles and maybe even longer through the use of that Inconel. I can go to some of these facilities where the boiler feed pump's 25 years old, never been changed. Other facilities like Pinellas, they just recently had to rebuild their boiler feed pumps. So heat exchangers, the tubes kind of foul and get corroded, and they replace them periodically. So I'd say the average equipment replacement cycle is somewhere between 5 and 20 years. Yes, sir.
It doesn't matter if you're at full capacity or not full capacity, right? Because the machines still have to run.
Yeah, the turn-down ratio, they can operate these facilities at like 75% throughput, But, you know, obviously, if you can run it at 90%, or 100%, you'll be able to pass more material through it and do more work with it. But no, you can turn it down to like 75%. Now, in the case of Pinellas, 3,000 ton per day facility, back in 2010, when the recession kind of hit and everyone bottomed out in terms of waste generation, they were shutting boilers down on the weekend, on Sunday. They ran out of fuel. So, oh, well, you know, if you run your equipment at a lower rate, then you get better performance over time, so it doesn't wear out as much. Pat? Yes, sir.
Hi, thank you. I have a couple of, I guess, statements and a couple of questions. You talked about air emissions and the need to address some of those components. Could you clarify what those air emissions that might be a problem for us?
You mean the regulated pollutants?
Yeah, you said that, and some of these need to be addressed, and I didn't.
Well,
hear what those were.
NOx, I think I tongue-in-cheek referred to this as the pollutant du jour. It's the one pollutant that's still fairly high
Yeah.
in terms of its limits, allowables, and it's under greater attention. For example, the state of California, as much as I love California, they don't want anybody having a more than 5 ppm NOx release. So, I mean, they've pretty much shut down the power industry in the state of California. That's why they're buying power from every other state, because they can't do it and meet their own rules and regulations. So NOx, that's where you're seeing more and more technology being applied. That's where the SCR came in at Palm Beach County. That's where the use of different and newer catalysts are being employed in Europe, where they're driving down those NOx emission rates. That's probably the only real parameter that's being addressed.
I know that in the Vancouver situation, which they have now abandoned the Waste2Energy, a big component of the opposition was around nanoparticulates going down to the Fraser Valley. And you may not know that specific story, but
you say the metals like lead and cadmium and
yeah,
mercury?
The claim was that there were particulates that were being emitted that they could not capture. And
Yeah.
that really brought that project to an end.
Well,
up there.
okay, so in particulate, PM is the parameter that we're talking
Parts per
about here.
million.
In Europe, they're using, well, I don't know if it was invented in Europe or not, but Gore, they have fabric filter bags that are high temperature polyethylene, poly-something bags, but they also now have catalysts embedded in them. So they're able to further remove certain types of pollutants with advanced technology. And reportedly, these bags have a longer life. So not only are you getting a better performance, but you're getting a longer cycle between bags. In answer to your question, the fabric filter bags oftentimes are changed every 2 years in America, whereas these Gore filter bags can last 5 years.
What is the percentage of ash that's emitted from the process?
About 20%.
Okay. My experience in Spokane is it's about 28 to 30%. So
Yeah.
20% would be an improvement. But that would still have to be disposed of and managed and the rest of it.
Right. Well, a lot of that percent is water, okay?
Yeah.
And then in Spokane, they weren't doing a stellar job of removing metals. That's why their guy in Roosevelt's now doing it for them. So you're seeing some metals in their 28%.
And the one thing I would point out, just from a numbers perspective, 4,000 tons a day at a facility would mean 266 round truck trips into and out of somebody's community. And I would think that would draw some attention. So thank you.
Yeah. Well, it'd be far greater number if they came in Packer trucks. That's why a lot of these communities are using those transfer vehicles. So 260, I bet you that's one every 5 minutes. I don't know, but you know, some communities have gone to barge delivery systems up in New York City where they have access to water and rail. So there are options. There's a community in Montgomery, Maryland. They tell me the wealthiest community in America. They have a waste energy facility. They built their own railroad, It's 7 miles long, and they've been shuttling one train a day for 25 years now, and all of that was done to keep trucks from going through neighborhoods. You get to choose in today's world. This is not Burger King, or is it? Maybe it's Burger King. Let's talk about the European.
I'm sorry, one more comment or question here.
I just have a question. It seems to me that in Palm Beach, Florida, with the high groundwater table, that there's very little alternative to incineration. It's not like they can build a landfill there. They don't have arid areas. Here we have the option of exporting waste to arid area landfills. And I was just wondering why King County would want to build an incinerator for $1.1 billion and be a hazardous waste generator for the first time, have to ship hazardous waste by rail to one of these export landfills when it has this other option. And also, going along with that, I was the project manager for the siting of an incinerator in King County in the mid-'80s. And the major concerns were that burning plastics in incinerators produces dioxins and furans, which are the deadliest compounds known to science. And I know that your filtering systems are effective at taking these things out, and they end up in the fly ash, which has to be disposed in a special ash monofill, which would also require waste export. But nonetheless, there's a public concern when they see that plume, even though it's just steam, that there are dioxins and furans in it. So that was a big concern. Then the height of the stacks and the visibility of the plume much of the time in the cool northwest was another concern, and the fact that they bring truck traffic into their neighborhood. The idea that a community would accept all this and then accept additional truck traffic from King County inviting other municipalities to send their waste to the King County incinerator is just absurd to me. I say good luck citing this in King County. I don't think it can ever happen.
So, ma'am, to your point, and I'll refer to Pat's opening comments, right? Our role here is to inform the discussion on waste to energy. We are not saying this is the solution for King County. We're providing the parameters of what waste to energy might entail for the community. The solid waste master plan is going to look at 3 alternatives, as Pat discussed. Extending the life of the landfill, potentially railing to eastern Washington, or waste to energy. The focus of the discussion that we've had so far is only to inform the alternative on waste to energy and what it might entail for the community. We are not, and it's not our role to decide that this is the solution for the county. That's a county decision to be made in the future. So this is just to inform waste to energy as an alternative, and we'll talk a little bit about landfill capacity and rail capacity for the second alternative. But we are not doing a alternatives analysis, making a comparison to determine what the solution is. Things like visual impacts as part of the State Environmental Policy Act decision and the National Environmental Policy Act, those kind of criteria go into the evaluation that the community would have to make in the selection of an alternative, right? If you say the purpose and need for the county is to deal with its solid waste in the future, then you have to go through the process based on evaluation criteria that are selected by the county to decide what the best answer for the county is. Our mission here is just to inform the waste to energy alternative. It is not to make a recommendation that this is the answer for the county. This is just informative to help the county move forward. This is the beginning of the process to determine what it wants to do. We are not saying what the county solution should be. I'm sorry, I can't hear you, ma'am.
I'll be back.
Okay. So we have provided some of those. I would have to defer to Paul on the dioxins and furans and the plastics and let these guys who are the experts on that handle it.
You know, I'm not really an expert on dioxin and furans, but I did bring a paper with me and read it on the plane. about some grad students from Columbia University who investigated dioxin furans and talked about how they have been significantly reduced from waste energy plants. But one of the things they pointed out, believe it or not, is that forest fires have now surpassed anthropogenic emissions of dioxin furans. Okay? So the increase in the amount of forest fires lately has now made them the #1 emitter of dioxins. And backyard burning used to be #1. And believe it or not, biosolids, wastewater residuals are also reported to have quite a bit of dioxin furans in them. So the landscape's changing. It's a complex subject, but waste energy really is getting much better at controlling dioxins. And lastly, we don't call them incinerators anymore. That was the term before we started recovering the energy. So resource recovery facilities or waste energy facilities is really how we address them today.
To change the subject a little bit, is the county's intention, if they were to build a facility, to have the trucking the same way that it is now, to where the garbage facilities would take them to the transfer stations and then the transfer stations would haul them to this major burning facility?
So I would defer that to the county. As we'll discuss in the recommendations, this is just a preliminary discussion of what a waste-to-energy facility might look like, what the best technology based on the situation for the county could be. If desired to be explored in greater detail, in our recommendations, we will talk about some of those kinds of things to help. But no decisions on siting. We weren't asked to do that, and therefore how the transport to get to whatever selected site is outside the scope of what we've been asked to do so far.
So the gentleman earlier hinted about Cedar Hills, right? That there was room up there. So
Potentially, but that's just one, just a frame of reference to show that it could fit there. We have in no way been asked to do any analysis on siting, make recommendations on siting, how the material might get there. Again, this is the first step. If the county were to choose this as an alternative, there would be much more work to get to transportation, to handle issues associated with the other environmental impacts. You know, the whole state environmental process to do purpose and need and scoping and alternative analysis and all those kind of things go into that as this process moves forward. But we're nowhere near a launching point for that. And this just generic discussion of waste to energy, the sizing, about the size of what it might be, could it fit there potentially? Is that the right answer for the county? That's not, we have done no analysis to make that kind of recommendation yet.
So for the record, I appreciate the forum, but to his point and the conversations I've been talking about earlier about more trucks coming in the facility, if it was to be at the Cedar Hills landfill, I don't see any different than what it is existingly for our existing garbage.
Right.
So the truck drivers would still, the garbage haulers would still take it to the transfer stations, and it would still be transferred just like it is now up to the Cedar Hills landfill. The difference would be the outside, to somebody else's point, the outside entities tried to come in to try to make more money.
And I think that was to Paul's earlier comment on much of the infrastructure, transfer points, truck routing is already in place. I would agree with that it might not have much of a change, but getting into the detailed discussion of that is beyond what we were asked to do. And this is what waste energy looks like. And now, if the county chooses to move forward, you get into all those very hard nuts to crack on where do you site it? What are the issues associated with the siting? That is all beyond the scope of what we've been asked to do at this point. This is really to inform the county in a way to help decide whether they want to consider moving forward as one of the alternatives with a waste-to-energy facility. And with that, we'll turn it over to hear the European side.
All right. I'm trying to phase this around right now because this is an important part of the whole discussion. It's the European side. And when we went out and looked at the research on for the European facilities and actually worldwide, we're discovering that there's a huge trend that's moving away from landfilling. European landfill legislations actually state to move away from landfilling for reasons of environmental concerns, of public concerns, of cost issues, of lost resources, to stay within the Kyoto objectives. Waste to energy is seen as the method to go and to move forward with. And you can see that by that currently there are over 2,000 waste to energy facilities operating worldwide. China is building an average of about 50 waste to energy facilities per year. They have over 450 right now. Europe has over 600 and are continuing to build as well, even though Asia right now is the biggest market. But the Middle East is adding facilities too that we didn't talk about, and so are different Asian countries, other Asian countries. The U.S. has 77 facilities, and for specific reasons, the waste going to waste to energy has reduced, where everybody else in the world seems to increase that. And when we looked at waste to energy in Europe, we had to consider, we looked at different criteria. And again, to build on what we're looking at, we were given the spectrum of the amount of waste that's going to be projected for the future. We got a lot of feedback from our European partners. They asked, well, is the waste really going to grow by that much? And I mean, it wasn't for us here to make that point. However, with recycling efforts and reduction efforts and so on, we might never really reach the 4,000, 5,000 tons that are projected. So we could be seeing reductions in that, and the question is not for us to answer building smaller facilities, what you see usually happening in Europe. The facilities that we looked at, this one is in Hamburg, Germany, and we looked at different facilities to move in with different criteria. This facility has been in operation for nearly 20 years. And process about 1,000 tons a day. And since 1999, the operation started, the city-state of Hamburg has been a zero waste to landfill city, almost 20 years. You're talking about oxidants, furans, and that's a discussion that came up, and I can address it briefly. They're no longer seen as an issue because they're taken care of. They're monitored around the clock. The emissions are made public via newspapers and public forums at least once a year for most facilities. And they're put in context. The governments have reported on this in Europe, saying dioxins and furans and waste to energy is no longer a concern. They're no longer a health issue. We don't have to worry about them. And this is a common fact in European legislation. Also, what's interesting about this facility is that it's been utilizing, as I said, zero waste to landfill. It's been utilizing the bottom ash. The bottom ash, and we're going to see that later on too, is very, they separate the metals, the non-ferrous out of it. They're able to use the bottom ash as an aggregate in construction projects. It has, let's see what we're forgetting, state-of-the-art flue gas, yes. It uses combined heat and power. There's an adjunct port to it that gets about 10 megawatts of energy. It supplies a factory that used to use fuel oil, about 80,000 tons a year, and now they're using the steam, and instead of that, replacing heavy fuel oil, reducing the carbon further. That was in Hamburg. Now we're looking at another facility that was in Rothensee, Germany. And you see there are like two things that look the same, and they started with one. And that was so successful that they decided to build another one. They wanted to scale up. They said, we have a certain amount of waste volume, we're going to build a facility right now. And it worked, it worked enough, and they found that there was more waste than they needed to. They needed more capacity for more facilities, so they built an identical one right next to it. Because we looked at upscaling, what can you do, and they just decided to build a second one right next to it. Total capacity of about 2,000 tons per day, combined heat and power. They utilize the bottom ash. It's another model, and you can see it's located right next to waterways. Same as the first one. Same as the third one. This is in Copenhagen. This is a new facility that went online this year. And the ski slope is supposed to open up at the beginning. They're hoping that they're going to have it operating in about March or April. And why I'm saying the ski slope is interesting about this, it has to be architecturally appealing where it's at. They wanted to make it they wanted to make use of it, they wanted to be integrating it into the public. The emission levels are extremely low for this facility as well. There are criteria, there are EPAs, there are regulatory frameworks that set these, and they're way below these. We talked about NOx levels. There are 2 facilities right now that are operating, one in Norway, I believe, and the other one is in Sweden. They have less than 5 parts per million on the NOx, which is almost non-existing. And we talked to the construction companies, so the builders of the technology. They can meet 2 parts per million criteria by just adding more filtration systems, more membranes to the SCR filters. So if it's desired, like in California, it's a possibility. And interesting about this one too is this is an integral part, as stated by the Danish government, of making Copenhagen the first zero-carbon city by 2025. Landfilling doesn't fit in that scenario. Waste2Energy does in this case, the way it's seen. Next facility we looked at is in Brescia, Italy. It's a facility that's been operating, I believe, for about 15 years now. Maybe not quite, about around 12 years. And as you can see, it's also an architectural concept. I've just drove by there again this summer, and you don't even see the smokestack when you drive by, the way it's integrated. Most of the time, you don't see anything coming out. If it's over 70 degrees Fahrenheit, it's because it's mostly water, about 99.99% water. So you just won't see that. It's stated with the Italian government that avoids 760 kilogram of carbon dioxide per ton of waste over their state-of-the-art landfill, which is adjunct, which they have right there. It also provides combined heat and power. The tipping fee is at $65, and it's a 1,600 ton per day facility. Another facility, and this is one where we talked about Vancouver, British Columbia, and was intricately involved for a long period of time in the discussions about valleys and smokestacks and polluting. This is a facility in Switzerland. This is where it's located. These are mountain ranges, just similar like what you find in Vancouver. This is a facility that's been in operation since 2009. I was so lucky to get a tour 2 days after it started operation from the Federal Minister of Environment from Switzerland, who was very excited about this facility. And it got architectural awards. It has extremely low emissions. And my favorite part, and I just saw it again this summer driving by, is there's are vineyards around here. There's agriculture right here. There's no problems. Why would there? I mean, Switzerland has about 34 waste-to-energy facilities. Most of them are located in towns and centers and valleys. Emissions coming from facilities today are no longer an issue like they used to be in the 1970s or 80s. They've been addressed properly. What's interesting about this is you can, and this has many facilities, you can also include wastewater, sewage in facilities. If you need to get rid of it, if you need to get rid of it, there's a certain way you can do that, and this facility does. This is another, a little bit more industrial-looking facility. It's a little bit older facility, but it's the largest in Europe, and this is in Amsterdam. So we're jumping all over Europe. You know, they have over 600 facilities. They're building more facilities. And what's interesting about this facility is it has 27 neighbor municipalities. You know, we have 39, but, 27 right there. It has the highest energy recovery of a facility at over 30%, and energy in the form of electricity. That's important to say. The more electricity you produce, the less efficient usually you are. So even though this facility is able to recover 30% net output, if you go into combined heat and power, you can get 70, 80% plus. But the focus on this one here was really to see how efficient you can design the structure of electricity efficiency. It provides power for about 300 up to 320,000 households, and it's seen as an integral part of the waste management system that recycles over 60%. I believe they're about 65%. So it works quite well. Another one that we looked at too, and that's very promising, this is in Oslo. They are the first in the world to capture carbon from a waste-to-energy facility. It's on a small scale right now. However, they have been very successful in doing so, and it's meeting the objectives that, the Paris Climate Agreements, climate being a very key factor for the Europeans. This is going to further accelerate and help also capture the additional carbon, that is still coming out of there. And this is going back to the Hamburg facility. I like to use it because it shows how efficiently you can use bottom ash. This has been done for 10 years ago. The project was implemented. The facility is right here. Over here you have a steam the steam was delivered. They built an underground tunnel in the construction, so it's about the planning. We weren't to look yet at the planning. That's not what we looked at right now. We could include that. However, this entire terminal here, you see right here, at the time right now they have built other terminals like this across the world. It has an annual throughput of more than Seattle and Tacoma combined in one terminal. The average trucker, we had a delegation from Los Angeles there of 54 people. They looked at this, and the unions in Los Angeles were really excited because the average turnover is 15 minutes per trucker. Because it's highly efficient, so they don't idle their trucks for 2 or 3 hours. So it made it all very interesting. The reason why I'm bringing this up, why we're talking about terminals, is because it's built on bottom ash. It saved 40% in the construction cost. It's right next to the water. It's a very user-friendly product. They had to, like, you know, how you have settling, they had to pull up certain areas once in a while. And every time they pulled it up, they were able to reuse that, close it up, no settling. So you can see the way it's designed here is you have the bottom ash at the top bottom. And we saw that with numerous delegations while they were still constructing parts of it. And then they just put a monotonous layer of asphalt on top of it. Here you can see some, looks like in the Tron movies, these bridges drive over each other, they move, it's all automated. It's quite a marvel. And here's just an application where you can see a machine just putting something on top of it. Also, this is called the cruise terminal. We're missing the I, it's the same thing. Cruise terminal is also in Hamburg, is built on bottom ash. And the interesting story is that they had overcapacity for the port of Hamburg, which continues to grow. It's the second largest port in Europe. It's one of the largest, 10th, 11th largest in the world. And they had overcapacity coming in. They needed to unload some ships. While this was constructed and was built on bottom ash, no top layers, they laid a whole bunch of, virtually within 24 hours after that was put down, the ash, they put containers on it and it didn't move because it was so solid in structure integrity. And then all they did, once they freed up the space and they continued the construction of the terminal, it continued to move on, and they just laid the layers on it. There was no settlement or anything like this. So now I'm going to turn it back over, unless if you have any questions on that. I think we're on the time. Yeah.
Okay, I'm going to talk a little bit quickly, actually, about bottom ash recycling and metal recovery. This little excerpt, this illustration shows that there's actually twice as much metal remaining in the waste stream after curbside recycling. And that's the red bars for ferrous and non-ferrous. So those metals historically are not recovered because they're part of composite materials. They might be parts of the ceiling fan or the toaster at home or various auto parts, things of that nature. So if we can recover 4% ferrous and 0.8% non-ferrous, it's equivalent to about 2.7% of your recycling, overall recycling rate. Right now, we're assuming 50% recycling rate without waste-to-energy. With the advanced metal recovery, 59.7, and if we can recover, let's say, 95% of the bottom ash for reuse, we can jump your recycling rate all the way up to 70.6%. And that's a pretty significant jump because, you know, what do they call it, the law of diminishing returns? You can make gains in recycling, and we have done so over the last 20 years just by implementing curbside programs and things of that nature. But going after and getting more and more becomes harder and harder as time goes on. But anyways, that's the potential that we're talking about. This is the second generation plant. These are most of the plants today. The Grizzly Overs, +6 materials, that always has the kitchen sink. The -6 materials, these are both recovered by magnets, ferrous metal recovery magnets. This is a pile of non-ferrous. In America, typically we're recovering the +3 A lot of this material actually melts and solidifies and turns into what I call a nugget. There's a nugget showing right there. And some of these other items are brass, bronze, copper, and that sort of thing that I've cleaned up and washed, just so you get a feel for the strange and mysterious parts that somehow fall out of the waste stream that are now recoverable. And I call that being liberated. The combustion process disassembles those types of materials, and with technology we can now get it out. Europeans they go beyond what we're doing in America. They're now recovering the glass and washing the glass. They're also recovering, you know, ferrous and non-ferrous metals, but they're going after fine particles. And you can see some of the various aggregates. They're screening and sizing the aggregates for different properties in road construction or sub-base and base type of applications. So Europe continues to lead the way. Here's some samples of various materials that have been washed, and these are what we call the fines, less than 3/8 or whatever, less than so many millimeters. But over here is another estimate of what types of precious metals are hiding in some of these piles. And that includes aluminum, gold, copper, iron, silver, zinc, lead, and palladium and platinum. And is there silver in there? There is. So the Europeans also are recovering precious metals and making handsome returns on that. Again, samples of some of what I call the white metals, the aluminum, of a certain size here, nicely cleaned, have high market values, especially to the mills. I know you have some aluminum mills in this area. You can separate the red metals from the white metals, and the red metals are worth about 4 times bronze and copper, and the Europeans once again are learning how to do this. So now talking about the use of bottom ash for recovery or recycling. When you pull all those metals out, now you've made your aggregate look like aggregate. It's not ash with a bottle cap in it or a Pop-Tart or a nail or a part of a metallic object. So it looks like the real McCoy, and it can in fact serve as a road-based structural fill, flowable fill. It can be used in asphalt and concrete pavements. And it can also be used as a feedstock for the manufacturing of Portland cement. And so the Portland cement is the gray stuff that you buy in a bag, and if you open the bag up, it always explodes into a dust bomb. That's Portland cement. That's what you use to make concrete. And so in the manufacturing of Portland cement, it needs alumina, ferric oxide, lime, and silica, and it just so happens that those ingredients are almost in the right proportion in ash. I'm not going to talk about combined ash for the moment. This is a map, an old map, of where all the cement kilns are located in the U.S. You have quite a few up in your area. There's one in Miami, Florida, where they did test burns back in 1993 using bottom ash, and it worked quite nicely. They're now thinking about implementing that program again starting in next year. Pasco County, Florida, which was just north of Tampa, they recently got permission from the Florida DEP to use bottom ash in road base, as an aggregate in asphalt, and as an aggregate in concrete. Concrete, that's the stuff we drive on. Okay, so that's in motion. Now, here's the opportunity for Portland cement. These are the 4 primary ingredients. Here's the typical range of percentage in Portland cement. Clinker is a term that they use. The clinkers are the little marbles that they make in a cement kiln, and then they grind it into a Portland cement. But anyways, you can see the typical waste energy ash is almost perfect in terms of composition for what they need in a cement kiln. So that's one of the things we think you ought to consider, is entering into some discussions with the local cement kilns to find out what their interest might be in using these types of materials. Okay, a golden opportunity. Now we're going to switch gears, talk about financials. So we developed this financial model, and we used a very conservative set of parameters because King County Solid Waste Department told us very clearly they wanted to know what the all-in cost would be. What is it they could expect to see from a project like this? So our capital costs we used based upon Palm Beach County as the reference plant. We adjusted for inflation. We bumped it up for the seismic zone here. We added the sales tax. We added owner costs. We added $5 million for site acquisition. That's just a place marker. We added $15 million for an advanced metal recovery equipment and building. And I must tell you that I went to Denmark recently and I saw ash being processed outside without a building. So go figure. you can do whatever you need to do sometimes. 1.35 million for the electrical interconnection, and we bumped everything up by 5% on a contingency. We had our 3 scenarios that all have different sizes. This one's a 4,000 ton per day unit, but it has 1,000 ton per day. I'm sorry, it has 1,000 ton per day units. This scenario had 1,125 tons, and this scenario had 1,050 tons. So they all had different base costs, similar, in the same range. The sales price of electricity, we used 4.9 cents per kilowatt. That's in 2028. Who knows what it will really be. But that number is equivalent to 3.7 today. We escalated the electric sales price at 2%. We assumed 609 kilowatt hours per ton. We assumed a 90-10 revenue share with the operator, and that's typically done in these facilities. But I will tell you that Palm Beach County, on their second plant, kept all the revenues. They didn't share it with their operators. So it's preference. It's the community's preference as to how they want to structure the deal. But if you incentivize your operator, you give him a slice of the revenues, the underlying premise is that he'll pay more attention to the plant and try to make it more efficient. Metal recovery, we're assuming 0.8% for non-ferrous, 4% for ferrous, $50 a ton for ferrous, $750 for non-ferrous, and those numbers are actually low, especially the non-ferrous, with some of the samples that I showed you of how they're cleaning those materials and segregating those materials into sizes, red metals, white metals, et cetera. There's more money to be made in the metals than I'm taking count for. No RECs or voluntary credit units. The state of Washington really doesn't allow them from Waste2Energy at the moment, so we're not taking any credit. No revenues from the sale of, I'm sorry, ash transportation, we're assuming out-of-county disposal, $54 a ton. Debt service, 5%. Hillsborough County just refinanced their debt last year, and they issued their bonds at 5%. And those are revenue bonds. Those aren't general obligation bonds. Construction period of 42 months. That's what it took for Palm Beach County. Maybe it can be done in 36, depending on the size and your weather and that sort of thing. So those are the parameters we used. We used an O&M fee. The contractor gets paid $23 in that range, depending on the size of plant. There's always economies of scales as you size things up. But remember, he's getting a share of the electrical and metal revenues here. So some people might look at those numbers and say, oh, those are way out of bounds. Those guys want $30, $35 a ton. Yes, they do, but they're getting some revenue sharing here. The county annual management costs, $210,000 a year. That assumes one new person, project manager, that just monitors this project continually. Environmental consultings, that's me. $350,000 a year. That's typically what a community will pay us to serve all the monitoring and operational issues over the course of a year. All right, now here's where we get into trouble with these escalators. And a lot of these escalators were in fact provided by the county for your region. We personally think they're high. If you look at some of these, like 3%, 3.2 on labor, 2.8, 2.8, 2.9, all of these escalators, when you blend them in, round out to be about 3%. That typically would mean, on the operational side, that your operating costs are going to increase by 3% every year. I went back and looked at Hillsborough County and Pasco County and Pinellas for the last 5 and 7 years, and they're averaging, these are all Florida facilities, they're averaging 2 to 2.2% annual O&M increases. Now, if your area continues to be a high growth area with high costs, then okay, maybe it's real. Right now, I'm a little bit nervous that we're overly aggressive in terms of escalators. So this is our first look at the cost for a 20-year cycle. And the majority, first of all, the high cost, $140 million, that has to be made up by what we call the tip fee, the Waste2Energy tip fee, which when you divide that number by the amount of waste that it processed that year, it's $126 a ton. That's in 2028 dollars. Now that's a big number, that scares everyone. But remember, it's $28 that have been escalated at essentially 3%. And then, when you pay it all off, first of all, it's a declining rate. Your unit costs are declining over time because you're filling your plant up over time with more and more waste. That's why your cost curve is coming down. Okay, so, but at the end of the debt service period, the last year, you fall off the cliff, so to speak. You drop the majority of your cost, in this particular case, are capital costs, and so you're left with just your variable costs, your operating costs after year 20. Now, Pat pointed out, and he's correct, this is just a 20-year snapshot, but it doesn't consider additional investment beyond year 20 for another facility or an expanded facility. But we're only looking at it from a 20-year perspective, and we thought it was important that you realize how much you can drop in terms of cost once you pay off your debt. Okay? A lot of communities around America have already suddenly realized that. Lancaster County is about to pay off their debt. Kent County, Michigan, they dropped their tip fee by 35% when they paid their debt off. Now you can take this 20-year machine and make it run to 40 and 50. Okay? So we did this now as part of an exercise. We took that $126.34 and we said, what does that's 2028 number. What does it look like in 2017 when you take all those escalators away? And now that number is 87.11. That's more in range with where you might expect it to be. It's still high, okay? It's a lot higher than a landfill. And it's hard to compete with a landfill. Trust me, you dig a hole. What's the technology there? So anyways, we sort of did that analysis for the 20-year and $2048, where I called it falling off the cliff. That number's $37.49, but in terms of 2017 dollars, it's actually $11.87. That's a bargain. And we wanted to just bring that out. We wanted to show you that there's a lot of difficulty in interpreting some of these numbers when they're that far out in time. So we did the same analysis for the 30-year plant, and the reason you start out a little lower, this was 126 in the 20-year scenario, now it's 109. The reason that's lower is because you're stretching your debt payment out over a longer time, so your annual mortgage, so to speak, is lower. And then at the end, when you fall off the cliff and pay your debt back, you're not falling as far because you stretched out your payment over time. And so that's what the 30-year cycle looks like. And then similar analysis where we took those 30-year or 2028 dollars and reduced it to 2017, and you can see what they look like in terms. And so that would give you a better number to compare what a waste energy might cost compared to your current system cost. Yes, sir.
I thought earlier that you talked about to rebuild the facility is every 5 to 10 to 15 years.
Oh, that's just pieces of equipment.
Pieces of equipment.
Yeah.
So, but that's not built into this cost, right? So where your revenue is just paying for the facility, it's not to rebuild the facility. Like you got a graph that goes out 30 years. Obviously, it's going to need to be rebuilt during that period of time, most likely.
So here's what we consultants say. If your contractor is operating and maintaining that facility the way he's supposed to, and you're watching him closely, and you're beating him up over it every year, you will not have to make a major capital investment for a 20 or a 30-year cycle. We're seeing this in Hillsborough County, Florida, where a lot of that equipment is still running after 27 years, and it's doing very well. Okay, now, for the 50-year analysis, we did consider that that's a longer spell, and there may in fact need to be a major influx of capital to rebuild portions of the facility. The cranes. A lot of cranes have been replaced in these facilities today because they got smarter. They're full of automated controls, and they're very sophisticated, and they have regenerative braking. I mean, some components are replaced just because it's the right thing to do, and there's a payback associated with it. Other things just flat wear out. And so in the 50-year cycle, what we did is, again, you see that the costs are in the order of $120 a ton, but they're dropping, and they're stable actually until year 25. And the reason you're only seeing a small drop at year 25 is because you just added 2,100 tons a day of capacity. You basically build half of a plant to catch up with your growth. And now your growth, your costs are going up, up, up until year 49, and then the drop off the cliff isn't, once again, as high. It's now down to $119. So those are the types of scenarios that we ran. And we also reduced the $2028 to $2017 for the 50-year cycle. And you can see that the 2017 numbers are 81, 66, 35, 22. The numbers get small because of the discount rate and the way, you know, the impact of inflation and escalation. I know a lot of this is confusing, and it took me a long time to really scratch my head over it. I didn't do this analysis. We have a financial planner that does this kind of work, and this is what she prepared. And now, just to put things in perspective, for year one of these projects, the electric sales account for 85% of your revenue stream. Your metals, non-ferrous, 11%, and your steel is 3.7. So metals are low order, but they could be more based upon what I showed you about the way the Europeans are cleaning and sizing and segregating them. And again, this represents 90%, 10% share of the electricity and 50-50 share of the metals. That could be 100% zero if the county chose to, but then your O&M fee will be bumped up by the contractors. But anyways, if you really want to focus on how do you get more revenues here, then we have to pay attention to that electric price. And that's where I want to go in the future here. In terms of cost, the majority of the costs are associated with capital costs and debt service. And then the O&M fee for the contractor is the second most. And then ash disposal and transportation is the third. And then the rest of the costs are really minor. So again, if we want to make something more affordable for King County, we have to drive down that capital cost. And the way to do that is either make the plant smaller or to do a more rigorous analysis in how we estimate the cost. Right now, this is high-level estimation. You know, we haven't sat down and made a material list and an equipment list and how many yards of concrete it's going to take and how big the pit is and all that kind of stuff. That would come with a more refined financial or feasibility study, okay? But anyways, remember, your two big ticket items are your electric revenues, your capital costs, and your debt service. We're assuming 5% interest loans. And so we thought, well, what could we do to enhance the revenues or reduce the cost? And so here's a couple items that we decided to look at. So we know we started your plant with unused capacity. That was the approach we took. So we said, well, what if we took all of that unused capacity and sold it for special waste at 50% premium? In other words, you would charge somebody 1.5 what you were paying to fill your plant up. Now, if you can find someone to do that, that would be great. And so we looked at it for two cases, to use all the unused capacity or to just set a limit of 10%, which is 400 tons a day, which is a lot of waste. Okay? So this might be a little optimistic. This might be pie in the sky. But I'll show you that with focused attention, you might be able to get there. Internal use of all energy valued at 6 cents. We've been told that in King County, for people that do analysis of your water, wastewater utilities, that they're typically assuming that you're buying power for 6 cents. That's your commercial rate, or industrial rate, actually. So we said, okay, what if we were able to use all the power from this plant for King County's water, wastewater, recycling facilities, public works, whatever you call it? And so we did an analysis of that. Now, can you do that legally? Maybe. If the facilities are side by side and owned by the common entity, King County, then yes, you can do it. You can move power back and forth without violating any Public Service Commission rules. And I showed you where Hillsborough County is doing that. Recycle bottom ash, 75%. we can use the aggregates, we can use the feedstocks for Portland cement, and then another is local ash disposal in lieu of remote landfill. I told you earlier we were assuming $55 a ton to transport and dispose of your ash to Roosevelt. Whereas if you had your own landfill, trust me, it doesn't take a lot of money or talent to put ash in an ash monofill. Most counties, they can't even tell me what it cost. Sometimes it's like $10 a ton. It doesn't cost a lot. Okay, so sale of renewable energy credits, if they were allowed, or additional electric revenue, 1 more cent. Suppose you were able to get 1 more cent, just a penny, 1 penny. Suppose King County had enough political clout that they could go to the local utilities and say, let's work a deal. We need a penny. Can you do that? I don't know. Get a law firm that specializes in this and give it a try. This is what it's all about, let's do some brainstorming here and see what we can do to try to drive these rates down. So these are the parameters we looked at, and here's a real example, Lancaster, Pennsylvania, where they added a building to especially, they themselves, with their own staff, Covanta runs this facility, Lancaster County runs that little building there. They bring in supplemental waste from Puerto Rico, out-of-spec pharmaceuticals, costumes from Disney World, you name it. They have full-time marketers that are out there providing that service for assured destruction, and I've been told that they make, and I don't want to be quoted, $7 million a year in additional revenues. Okay? One little county. Special waste in need of secure disposal can be a significant source of revenues. Okay, so let's count the ways. Unsaleable manufactured products, out of spec or out of date, discarded pharmaceuticals, industrial liquid and solid waste, international waste, regulated garbage, auto shredder residue, wastewater treatment biosolids and discarded fats, oils, and greases, used tires, used motor oils, and lubricants. These are just some of a long laundry list of what some of these facilities have learned how to market their services for. Only if they have excess capacity. If your plant's filled up with your own garbage, you're not going to have a very robust supplemental waste program. But anyways, the point I'm making is we're using this as an option. Okay, so what are the results of all? Oh, Hillsborough. This is where I live. I used to work here for 3 years. So Hillsborough has an adjoining wastewater treatment plant. It's not a big one. It's 12 million gallons a day, and it uses 2 megawatts of electricity. And then they have a water treatment plant up the road, and the water treatment plant doesn't use much power either. They're thinking about providing additional power to their public works campus, and that would be 5 megawatts. So at best, Hillsborough County can divert 7-8 megawatts of their power to their own needs and save a lot of money, but they're still selling 37 to the grid. And this is their campus, and I call it a public works campus. It has a jail, it has the waste-to-energy facilities here, the wastewater treatment plant here, they have a bunch of admin offices here, they have a yard waste processing facility here, they have more facilities up here. They're talking, and there's the water treatment plant there. So they own all this property, it's 240 acres, and they want to power it all up, okay? And so this is very similar to a concept called a microgrid concept that's being promoted by the DOE. And microgrids are being designed now because all these natural events, Superstorm Sandys, hurricanes, when the power goes off, the water goes off, the wastewater goes off, everything goes off, traffic lights go off. So they're trying to come up with more robust designs for these microgrids where critical infrastructure doesn't all go down together. And so therein lies an opportunity. The DOE is actually paying people to do these feasibility studies. They'll pay you to look at concepts like this. Here's the summary of our sensitivity analysis. If you were to fill that plant up with all your excess capacity in year one, you could generate $56 million. Now that is a little hard for even me to believe, but nevertheless, that's the way the numbers worked out. If you filled that plant up at 10% of the capacity, 400 tons a day with supplemental waste, that's still a significant number. $27 million in savings or in increased revenues. Internal use of electricity at 6 cents. That's a big number. If you were able to use all of that power, now remember that power is about 75 megawatts. I don't think you don't have any infrastructure that takes that kind of power. Maybe together it does, but now if you were to try to power up all of your facilities here, you have to go before the Public Service Commission and get special approval for those kind of things. Because the only people that can sell power in the United States are the regulated utilities. So again, this is a little optimistic. It may not be realistic, but if you don't try, you don't succeed. Recycle 75% of the bottom ash. That could be worth $11 million in avoided disposal costs. And that doesn't even account for maybe you might be able to sell some of those materials, especially to the cement kilns. They're buying all that alumina and ferric oxide and that sort of thing. They just might pay you if in fact they agree that they can work with it. Local ash. And so these are the results. And again, this is graphically kind of illustrates it better. This is filling up with supplemental waste. This is 10% supplemental waste. This is internal use of the power and the various others. So again, it gives us a feel for where to put your attention if you want to drive costs down or improve revenues. There might be other parameters we could look at. We did look at reducing the interest rate by 0.5%, and it doesn't really amount to a lot. Okay, so I put this little graph together to say what combination of things in terms of sensitivity could you do to really result in either improved revenues or reduced cost? What would be the net gain? What's it worth? And in this particular set of where we're accounting for 1, 2, 3, 4, 5, 6 different parameters, we're able to affect a 70% reduction in your tip fee. Now that's really optimistic. This case here I called optimistic, where we have 1, 2, 3, 4, 5, 6. 6 of these. Is that the same one as? No, I call this one the best case, and in this particular case, your tipping fee would be $36.92. The next one isn't isn't as profitable, so to speak. This combination of events results in $73.49, and then these are $28, and that's again where we start to get a little confused with our own numbers. And then I say this right here is under the control of King County. They could market the supplemental waste, 400 tons a day, and dispose of the ash in a local ash monofill. It shouldn't be too difficult. Okay, and that would result in a tip fee of $93.38. So there's various combinations. You can study it more in terms of our presentation. The conclusions. It's a conservative analysis. We used a lot of high escalators. We feel that we can refine these if you were to do a full feasibility study. It's a large facility. It's oversized by anywhere from 28 to 45%. We used a modest sales price for electricity and the metals. And so if you were to proceed and go forward with a feasibility study, you could look at starting your construction earlier, lowering your capital and O&M costs, looking at some higher revenue streams, and then report all the costs in 2017 numbers. That's kind of what we think we would recommend at this point. And Curt's going to finish up, and I'm sorry if... Oh, do we have some questions? Go ahead.
Hi, thank you. Going back, there's a couple of things. Going back to the $126 number, that was to pay down the cost of the facility.
Correct.
But King County has a cost to run the system. That's not included in that.
Correct.
So it would be that number plus what King County needs to run the system.
Yes, that would. See, We shouldn't call this a tip fee. This is the
Right.
waste energy O&M, or the
That's the cost.
cost per ton.
The cost
Right. And then the
per ton.
overall system tip fee would be blended.
Right, okay, so that number is significantly higher because we've left out the King County number.
Yeah, yes.
And then the other point, then you do have an asterisk about it, at the 75% recycling ash. And I don't know what slide that was on. You have an asterisk that says that's going to need, that one there.
Yeah.
Would require statutory change. That's important for everyone to know because that ash is produced now in Washington State and it has to go to a monofill.
Correct.
And those legislative changes would happen. So they may not happen. They may be difficult to overcome that regulatory
Correct.
piece. And
But
then
in Florida, they've
Yeah.
already gotten permission.
Okay.
They put science together, and they had the right approach and test programs, and they did get approvals. And Philip will tell you in Europe that they do it all the time.
people have been trying for years in Washington State to get that changed, and it hasn't been successful. And then my other point from the report, so the capital cost to do this is $1.1 billion. Is that correct?
Yes.
I just have a hard time with King County looking at that $1 billion number when we have such pressing social needs and other needs in the county. But
Well-
I didn't see that in this, but that's the capital cost number.
That's correct. And I think that number's high because of all the escalators.
Yeah.
And the fact that we didn't do like a real fine-tooth cost estimate and breakdown of components and equipment.
Yeah. Okay, thank you.
But it was meant to be, and I hate to say worst case, but you know, in the engineering world, we have a base case and we have a best case and a worst case. And in this case, I called it a very conservative case, but it essentially would be your highest cost.
I had a question regarding the design. I believe you referenced a site in Florida that had some additional air quality treatment. Was it ACR or something like that?
SCR, correct.
SCR, pardon me. And I noticed you decided to not include that here. What would be the construction cost if we did include that additional air quality treatment? Do you know?
It's probably like $30 to $40 million.
Okay, thank you.
And that's part of the reason why I didn't recommend it, because in Florida, they sort of got pushed into a corner by the DEP. The DEP was being a little aggressive, so to speak, and got away with it. But they didn't have statutory rights to do what they did, but the county chose to just go along with it. It's the way the world works. Philip, you wanted to say something?
Yeah, just a couple points. On bottom ash, for example, we worked with Caltrans back in the days, about 7 years ago, and it took us 3 months to get the approval for use of bottom ash. So legislative changes are very likely. They can easily be done. SWAN and the Solid Waste Association of North America also is looking at pushing forward now with accepting the use of bottom ash as part of the recycling criteria. That to be said, one. What is important to understand too, because we're looking at really high cost right now, and that is an analysis that we considered very conservative, which means it's very high. It's probably the highest scenario that you can see at the numbers that you saw right there. If you would proceed with the project today, the numbers need to be put in realistic terms. They need to be looked at what are the real costs for today. And we tried to do that with our 2017 numbers, but we need to make sure that this is like a sensitivity concept too, where we look at tipping fees. I believe, where's Palm Beach right now? It's at $69 for a 3,000-ton facility. That is something to consider. That's where they're at with their, you ask about SCR, what does it cost? That's including the higher technology aspect of it. And in addition to is the other part is today you would not build, that's what the European side told us, and I'm in charge for the European side, you don't build overcapacity when you build a facility. You stick to the volume that you have today, you look at what you can recycle, how you can increase that, and then you deal with future waste volumes when they arise. So it's important to consider that you don't build a facility with overcapacity. It's very unlikely to be done. So just for consideration that. So that drives the cost substantially down on the tipping fees.
Thanks, Phil. Go ahead. Okay, so in the interest of trying to get us done on time, Let me get to the end of this. We were also asked to take a quick look at capacity for export. And so there are really two pieces that go with export, and one is the capacity of landfills in the region, and the other is the haul capacity to get it there. So very quickly, the county did a study of this a few years ago, and they actually looked at 7 different potential landfills for the county to export to. One of those 7 never got built. 2 of those 7 have restrictions that say only that community can use it, and therefore you're left with 4. So these are the 4 that you can see here, 3 in the Columbia River Basin and then 1 down in Idaho, Simcoe. If you take a look at the remaining capacity for those landfills, based on their most current reports that we were able to find, and in most cases those were at presentations that were given to the counties that were placed publicly because the landfills are sensitive to telling outsiders how much capacity they have. So this was based on reports to the counties and communities where these landfills resided. And so there's anywhere between 35 and 140 years worth of capacity in these different landfills based on their current loading. And there's more detail of this inside the report. Rail capacity, taken from the Washington State Rail Plan, the concern is that in the out years, reading by 2028, that most of the rail lines that feed those 4 landfills will exceed their capacity based on the planned rail loading. Another way to see that, here are those lines with the current loads, and there's a scale on the bottom that you can see where they are relative to 100% of capacity. And when you get out to 2035, within the life cycle that we're talking here for these different options for waste to energy, most of those lines, especially the western and southern route going from Seattle down towards Portland and over, is oversubscribed. Most of that line will be over 100%, and in many cases over 130% of the capacity of the rail line. Now, supply and demand says that if there's not enough supply to meet the demand, the price goes up. And so we didn't do analysis of the cost of that, but if you don't have the capacity to meet the need, obviously the price per ton to ship the material will go up as well. So just a caution on the export, there is capacity in the state, in eastern Washington, to take the county's waste if that's an option that the county chooses. We would warn that unless there is much improvement to the rail capacity in the same period, that the cost to ship the material as the capacity on the lines is exceeded in the future will go up. So that's really short, and that we want to get back to our recommendations on the waste to energy option. As we discussed at the beginning, we did a cursory top-level review of what a waste to energy facility might look like for King County without going through all of the scoping process to site it and look at all the other factors that would go into that. Just for a generic facility, we determined that mass burn, right, combustion on movable grates would be the best fit for the county. And in order to explore that, there are several things that would need to be done before you could refine the pricing, determine the siting, and we'll make some recommendations specific to that to do the feasibility study for it. And through some of the questions that we've heard today, it becomes clear that if the county wanted to do this, there would need to be an education process put in place to explain some of the pros and cons associated with waste to energy facilities. And with that, to talk about the feasibility study components to get into more detail on costing and siting waste to energy, I'll return the mic back to Paul to finish that out.
Okay, I'm going to be quicker than I was in the past. So we've already talked about the best fit. One of the things that I would recommend we look at here is the analysis of your existing conditions to determine compatibility with a waste-to-energy anchored system. And so, for example, you have 8 transfer stations. We've only talked about 1 waste-to-energy plant. It could be 2 or it could be 3 for as much waste as you have. What if that one facility, what if a small facility was close to a transfer station? Well, then you may not need that transfer station anymore. There might be system savings depending on the site-specific locations. What if, well, let's see. I was thinking there was another example of where your system might be reconfigured. By the way, where I live in Hillsborough County, Florida, just this year, the county finally figured it out that running their transfer trucks at night would increase productivity because they're stuck on the interstate system most of the day. And so they're now running trucks at night. And the facilities are open all 24/7. So there's no hardship in bringing, spreading the load out over time. And then analysis of options for the appropriate sizing of the facility. Sizing affects cost, cost affects affordability. I wanted to point out a couple things here. Evaluate the potential for treatments such as standalone anaerobic digestion facility. Well, that's for food waste and organic waste, high-strength organic waste. That could be diverted to a digester. Some of your wastewater plants may have digesters, they may have capacity, or they could be modified to, you could get your wastewater brethren to get in the game with you as take on some of your solid waste into their system, so that frees up some capacity for you. There's other new technologies out there that you might want to look at. As part of an integrated system and a part of an integrated campus, there's a new waste plastics to liquid fuels facility in Akron, Ohio. It's being marketed by a company called Vadex, V-A-D-E-X-X, okay? And so they could, and we hear about the green sword and the green fence in China and the lack of markets for recyclables that are coming down the road. And maybe here, maybe affecting your communities right now. So if you can divert some of those waste plastics into another market, that might drive down the amount of waste you have to process through your waste-to-energy facility. And there's all kind of new technologies out there that are little pieces. Okay, so I'm not going to really go through the rest of this. These are just elements of a feasibility study that would go into detailed analysis. We would look at, that's where we would look at the siting and architectural options. And we would look at the priced energy, the availability of local markets, technologies for processing small amounts of your excess waste, whether it's additional composting or the waste to biofuels, those kind of technologies. E-waste, e-waste has far more value in terms of recycling revenues than burning it. And so, you might want to look at some of those things and just take apart the system a little bit more. I want to show you one little diagram, and this is my pipe dream. I drew this 25 years ago when I first got into this business. And I went around to all of the facilities for the company that I worked, which was Ogden Projects, which is now Covana. And I saw that one plant was doing this, and one plant was doing that, and another plant was doing this. And so I try to put it all together in my own mind, like, what can we do here? And so this diagram is, in my mind, an integrated solid waste management system, but it includes water treatment facilities, which, as we saw in Hillsborough, they're sending power to these facilities, and we could in fact have an anaerobic digester that's either associated with the wastewater or a standalone. And we have compost facilities, and we could have wood waste and used tire shredding facilities, and we can have an aggregate ash processing facility. And as you saw from what we presented today, it's real. They're doing this in Europe today. We could have a mixed waste processing facility. In the old days, we called that a dirty MRF, where you could take one of your transfer stations and convert it to a dirty MRF and make a product known as engineered fuel, which may in fact be something of value that the cement kiln would want as a fuel, not as a mineral, but as a fuel, and or other facilities, standalone power producers may in fact want to procure that as a substitute for coal or co-firing with coal. So there's a whole host of activities. And then we have, of course, you have your complement of landfills that are alive and well, and then you have your closed landfill. And I know you can't read this, but part of what is shown there is you could mine the old landfill for combustibles to recover capacity or space in that landfill. And that's been done. It's been done in a few locations in America. And you can take the leachate from that closed landfill and use it for processed water. And by the way, EFW is just another version of waste energy. It's energy from waste. And then you could have a steam and a hot water chilled loop for industrial combined heat and power. And so in a nutshell, I don't have an electronic waste recycling facility in here, and I don't have a waste of biofuels in here. This is still a work in progress. You get to pick. You get to design it. It's your community. What do you want to do? How do you want to manage your waste? And so all I'm saying is, here's a snapshot of what it could be, and it could be even more grandiose than this.
So, thank you very much, Paul. I think our microphones are fading on us here. I just want to recognize that we're about 5 minutes over, and I anticipate there might be some additional questions that you might have. So before we put a complete wrap on this, are there any additional questions for our panelists here that you'd like to ask? Okay. I want to thank our colleagues here from Normandeau, from CDM Smith and Neomer for the research that you've done and the efforts that you've put forward to kind of answer the question, what is the best fit waste-to-energy technology? I think this has really been helpful to inform the beginning of this dialogue. And as it's been stated a number of times today, this is that beginning of that dialogue. And I appreciate you investing the time to be here today and hear directly from the experts of what their findings and recommendations are. And I'll look forward to continuing this dialogue in our region as a key component of our comprehensive solid waste plan. I actually believe that this long-term disposal question is arguably the most important and relevant policy decision we have to make in this next operating period. So really appreciate you taking the time to be here and to educate yourself on some of these findings, and you can also count on being a part of this robust dialogue as we go forward. So thank you for your time. Again, thank you for the work that your companies have done. And I want to remind you that if you did not get a hard copy of this presentation, it will be downloadable. We'll have it on our website along with the video. We've videotaped this entire segment so that you can watch and share with others as well. So fear not, if you didn't catch some of the data on some of these slides, you'll be able to gain full access to this presentation on our website. So thank you again for being here today. Drive safe, stay warm, and have a great afternoon. Thank you.